quick review on how to do stoichiometry problems using the ideal gas law. So before we can do that, I just want to review the mole map quickly with you, in particular as the mole map pertains to balanced chemical equations. You might recall that the mole map allows us to go from a certain quantity of one species to a quantity of a different species, with a mole ratio in between. And I'm not going to go over the fine details of this map because we've seen this before, but we're going to use this to answer stoichiometry problems using the ideal gas law. We'll see that it's still applicable. So the first question that we're going to look at is this one, which shows a combustion reaction in which you're being asked how many grams of oxygen are needed for the complete combustion of a certain amount of propane. And I see that we're given 5.53 grams of propane. So we need to go from grams of oxygen to grams of propane. But before we do that, we have to make sure the equation's balanced. So I'll just go ahead and balance it for you. Remember that when we are trying to balance combustion reactions, it's always best to leave the oxygens for last. So I'll start with carbon. We see that we need a coefficient of 3 for carbon, and because there's 3 carbons on the reactant side, we'll put a 3 in front of CO2 to balance the carbons. We see that there's 8 hydrogens on the reactant side, so we'll put a 4 in front of the H2O. And lastly, we'll count the number of oxygens on the product side. We see that that's 6 oxygens plus 4 more, that's 10. And so we'll put a 5 in front of the O2 to balance the oxygens. At this point, we can actually go about trying to answer the question about how many grams of oxygen gas are needed to complete the combustion of 5.53 grams of propane. So if we look at the mole map, we see that we're given a mass. In particular, we're given a mass of propane, and we need to figure out some way to get over to number of grams or mass of oxygen. So to do that, we're going to go from mass to mole using the gram formula mass. We're going to go from there, from mole of propane, we're going to use the mole ratio. In particular, we're going to use the mole ratio of propane to oxygen, or oxygen to propane. Once we use that, we'll be at moles of oxygen. To get to grams of oxygen, we'll use the molar mass of oxygen. And again, once we use that, we'll be at mass of oxygen. So here's the plan. We're going to start with the mass of propane. We're going to use the molar mass of propane, multiplying by 1 mole over the molar mass of propane. At this point, we're at moles of propane. To get from moles of propane, we need to use the mole ratio of propane to oxygen, or oxygen to propane. That's 5:1. At this point, we're at moles of oxygen. If we multiply by the molar mass of oxygen, we'd be calculating the mass of oxygen that would be needed for the complete combustion of 5.53 grams of propane. So that's a simple application of the mole map. We can use the mole map to go from, in this case, mass to volume of oxygen gas at STP. So looking at the mole map again, so I'm given a mass of propane. And so to get from mass of propane, I need to go first to moles of propane. Then I'm going to use my mole ratio of oxygen to propane. That'll get me to moles of oxygen. And then finally, to get to volume of oxygen, I'll use the 22.4 liters per mole relationship to get to volume of oxygen. So there's the plan. So we start with the mass of propane. We'll use the molar mass to get to moles of propane. At this point, we'll use the mole ratio of oxygen to propane. And lastly, to get from moles of oxygen to volume of oxygen at STP, we'll use the 22.4 liters per mole relationship. And we've seen this particular type of problem many, many times before. The problem with this type of question sort of appears when we're not at STP. So, for example, what volume of oxygen gas at 25 degrees Celsius and 1.04 atm is needed to complete the combustion of 5.53 grams of propane? Now, those particular experimental conditions, 25 degrees Celsius and 1.04 atm, that is not STP. Remember, STP is 0 degrees Celsius and 1 atm. So we're not dealing with STP here. So there's a different way to go about this problem, but you'll see that it's very similar to working the problem out if we're at STP. In fact, we'll go about it virtually the same way. So what I'm showing you underneath this problem is the way we worked it out at STP. To calculate what the volume of oxygen gas is at 25 degrees Celsius and 1.04 atm, we'll go about solving it almost the same way. But in this case, we can't go. Let me just stop for a minute. So we'll look at what we have above. So at this point, in particular, right here, if we stopped right here, we would be at moles of oxygen. You can see the way we worked it out above. To get from moles of oxygen to liters of oxygen, we used 22.4 liters per mole. And that got us to liters of oxygen. That only applies if we're at STP. Since we're not at STP, we need to use a different way to get from moles of oxygen to liters of oxygen. And for that, we need the ideal gas law. So the way we do it is we calculate the number of moles of oxygen, pretty much the way we did it above, except we can't use the 22.4 liters per mole relationship. We have to use the ideal gas law and solve it for volume using the temperature and pressure that's given in the problem. So, since we've calculated the number of moles of oxygen, we can use that in the equation V equals N RT over P, and we plug in all the information. And just looking at our units here, we'll see that moles of oxygen will cancel with mole in the R constant. We also see that ATM will cancel, and we also see that Kelvin cancels. So we know we're going to be calculating liters here, and just going about the calculation, we'll see that we get 14.8 liters of oxygen. And again, the only difference here is that instead of using the 22.4 liters per mole relationship, we use the ideal gas law to calculate volume. Now you might be wondering, why does it need to be so complicated? Why do I need to do different things whether I'm at STP or not? Well, in fact, we could have used the ideal gas law to calculate the volume of oxygen gas at STP if we wanted to. A little bit more complicated to do that, but you'll see if we went about it the same way that we did in the previous problem and calculate moles of oxygen, we could then use the ideal gas law, this time inserting the temperature and pressure for STP. And doing that, you'll see that we get exactly what is calculated using the simple 22.4 liters per mole relationship. A little bit more complicated using the ideal gas law, but if we wanted to be consistent, we could use the ideal gas law every single time. Another problem. What pressure of Cl2 would be needed to make 75 grams of C2H2Cl4 at 20 degrees Celsius in 2.5 liters, or in a 2.5 liter container? So you see, what we're given a mass of C2H2Cl4, a mass, and we have to go to a pressure. So the only way to get to pressure of Cl2 is we have to first figure out a way to get to moles of Cl2, because if we can get to moles of Cl2, we can use the ideal gas law to calculate pressure. And so to get to moles of Cl2 from mass of C2H2Cl4, we go about it this way. And you see, what I've done is I've went from mass of C2H2Cl4, use the molar mass of that compound, and then use the mole ratio of Cl2 to C2H2Cl4. And you see we calculate 0.893 moles of Cl2. Again, what we're trying to do is calculate the pressure of Cl2. How do we get there? We get there through moles. And once we're in moles, we can calculate the pressure of Cl2 by using the ideal gas law. And so we solve it for P. P is equal to nRT over V. We simply insert the information that's given, and we get 8.6 ATM. So again, what we've done is to get from a mass of one thing to a pressure of something else, we've gone through moles. So we calculate moles of Cl2, and we use the ideal gas law to calculate the pressure in this case. Last problem. What volume of Cl2 measured at 10 degrees Celsius and 2.0 ATM is needed to produce 10 grams of potassium permanganate? So in this case, we're given a mass of potassium permanganate, and we're asked to calculate a volume of Cl2. So how will we get to a volume of Cl2? We have to first figure out a way to get to moles of Cl2, because once we get to moles of Cl2, we can then use the ideal gas law to calculate a volume. So just using regular stoichiometric procedures, we'll start with 10 grams of potassium permanganate. We'll use the molar mass of potassium permanganate to get to moles. We'll use a mole ratio of chlorine to potassium permanganate. We see that we'll calculate 0.0633 moles of chlorine. The question asks for volume of Cl2. So we have moles. To get to volume, again, we'll use the ideal gas law, solve for V, for volume. V equals nRT over P. And we'll simply insert the information that's given in the problem, and we get 0.74 liters of Cl2. So in all of these problems, what you've seen is that we're given information about one thing and either ask for the pressure, volume, or temperature of something else. The way to go about it is to go from the given information and calculate moles of that other species, and then we'll use the ideal gas law to calculate either the pressure, volume, or temperature, depending on what's being asked.